Lecture 53, length in spacetime. Now I have to apologize ahead of time. There'll be a bit of algebra in this. There's really no way to get around it. How do we measure length? So if I put up a point, and put it right there, okay? I make this at x equals 3, and this point here will be y equals 4. These are spatial dimensions, okay? Our concept of length, right, is based on the Pythagorean theorem, right? Length is always a positive quantity, okay?
Okay.
And it's a quantity that does not vary, right? So this meter stick, for example, is 1 meter of length regardless of what coordinate system I put it into or what orientation I hold it, right? Still a meter, it's length, right?
Yeah.
Here its length is a meter, right? Doesn't matter. Whatever translate, it's still a meter, right? So that's what's kind of fundamental about length, is that it's this quantity which is invariant, okay?
Okay.
So how would we calculate the length of this? Well, it's just a point, but what I mean is the distance from the origin is what I'm thinking of as the length here, okay? So here's my origin, right? This, I want to know what this length here is, called L, right? That's what we use the Pythagorean theorem. We say, well, you know, we can construct this little right triangle out of it, where this is of length 3, this is of length 4, right? L squared is equal to 3 squared plus 4 squared, and everybody knows this, right? This is the famous 3, 4, 5 triangle, yes?
Yes.
3 squared is 9, 4 squared is 16, 9 and 16 is 25, and therefore the length is the square root of 25, which is 5, right?
Yeah.
We always pick the positive root because lengths are always positive quantities, okay?
All right.
If I had flipped this around and had this minus 3, 4 over here, it would still be of length 5, okay? What if I rotate this whole thing by 90 degrees? So I can imagine taking this little triangle, right, and rotating it to 90 degrees. So that brings this point here around 90 degrees up to here at 3. I'll draw another figure. So now I've got this point at 3. This point here, as it rotates around, is going to go to minus 4. So here I have minus 4 and positive 3. So it puts it right there. And I want to measure this length, right? And again, right? So I've got length minus 4. This is length 3, right? This says that L squared, or this is L, is equal to minus 4 squared plus 3 squared. I guess I could have left parentheses off that one. Still going to be square root of 25 or 5, right? This is what we mean by lengths are invariant. Under rotations and other types of coordinate transformations, the length doesn't change. It's independent of the coordinate system we put down on it. Even if you change the unit, it's still, you know, this long. That hasn't changed. The number you assign to it may change if you go from, say, meters to centimeters or inches, okay?
Okay.
But the fundamental notion of this thing has a length that's like this doesn't change. Does that make sense, everybody? Good. Let's see if the Pythagorean theorem works in spacetime, okay? And so to do that, we're going to consider something like this. We'll consider a spacetime diagram. This will be t. This will be x. And I'll pick some point. Okay, we'll of course draw a little light line. I can pick the point here if I wanted to. It doesn't matter where I put the point. And then I'll draw my t prime axis. And symmetrically I get my x prime axis, right? And so in terms of the x coordinates, x and t, right? I've got this distance x here. And then the height of this is some height t. And we can imagine that this length we're trying to draw is like this. I don't want to draw, it's going to just make it messy. But to see what that is in x prime and t prime, we have to imagine these coordinates like so. Right? So I'll have some x prime measurement here and some t prime measurement here. Right? Now let's see what that looks like. So we want to say x squared plus t squared is equal to x prime squared plus t prime squared. That's pretty straightforward, right? Well, to see if this works, what we're going to do is we're going to use the Lorentz transformations on x prime and t prime. So let me write those down real quick. X prime, as you recall, is gamma x minus vt, and t prime is gamma t minus vx. Right? That's the coordinate Okay, so we have to substitute in. I know, this is why the algebra is messy, because we have to substitute in. When we have x prime here, we're going to substitute this in. And when we have t prime here, we're going to substitute this in. Okay? So let's see where that takes us. And I'm just going to write my equal sign over here, right? So I'm just rewriting this. So I'll get a gamma squared, and x prime squared is going to become x minus vt, quantity squared. I already squared the gamma because of this square here. Add to that t prime squared, so another gamma squared, this time t minus vx squared. Okay, now I've got to square each of these things, and so that's going to be equal to gamma squared. Where am I trying to get? I want it in the end to say that x squared plus t squared. This is, on the right-hand side, I should get equals x squared plus t squared. Okay?
Okay.
That's where we're trying to get to. Where was it? Oh, yeah, so I'm going to put parentheses around this because we got a gamma squared throughout. So I'm just going to pull that out, so to speak, right? And so inside, we'll have x minus vt squared, well, that's going to be x squared plus v squared t squared, and then we'll have a minus 2vt, right? Because we got minus vt, minus 2vxt, sorry. Right? X times minus vt, and then another x minus vt will give me minus 2vxt. All right, that's that one. Plus, I'll have this term. So I have t squared plus v squared x squared, and then similarly I'll have a minus 2vxt, all times this gamma squared. Okay, well, that doesn't seem to be going in the direction we'd like it, because see this and this, it'd be nice if those had canceled, right? But we can keep going a little bit, I suppose. So this would be gamma squared. This would be gamma squared times, and I think what I'd like to do, I know it looks messy, right? I see an x squared here. I see an x squared here. I'm going to do the usual algebra thing and collect like terms. So I bring these two together. I get x squared plus v squared x squared, right? Just collecting the x squared terms. I can do the same thing with the t squareds. So I have plus t squared plus v squared t squared. And then I got these two terms here, which are just going to add. So become minus 4vxt, all times gamma squared. And if I look at this, right, I can kind of see that, well, I can factor out x squared out of both of these. What is that going to do for me? Gamma squared. That's a horrible bracket. That's going to, I can take x squared, right, and multiply, factor out an x squared, leaving 1 plus v squared in there, right?
Yeah.
See that? I can do the same thing here. And then I've got this minus 4vxt. Okay, looking at that, I see my x squared plus my t squared here, right? That's where I'm trying to get. Okay? And I know, also I got to get rid of the gamma squared, right? This gamma squared has to go because there's no gamma squared on the left side of this, right?
Yeah.
And so far I'm not seeing any way to get rid of it. And this minus 4vxt at the end here is totally a problem, right? That's not going away. There's nothing that can happen here that's going to make that disappear. So I see we're already in trouble, right? So Pythagoras, rather, is in trouble with spacetime. But we can charge ahead and see if we can get any closer. So this will equal gamma squared. You see I can factor out the 1 plus v squared out of both of these terms. That's a little hard to see. Beginning algebra students usually have trouble with this kind of thing, but if you imagine in your mind replacing 1 plus v squared with, say, a, then I'd have x squared times a plus t squared times a. Obviously I can factor out the a, right? And have it be a times x squared plus t squared, right?
Yeah.
Well, we can do that here as well. So we'll get 1 plus v squared times x squared plus t squared. And I've still got this annoying minus 4vxt at the end here, right? And so this is what I want to get, right? This and this are the things that need to disappear in order for that to happen, okay? They're not going to disappear. And the reason why is because the Pythagorean theorem doesn't work in space-time, okay? This is one of the bizarre, I think it was Minkowski that first observed this. I'm not sure if that's exactly correct, but Einstein may have known that this was the case, that Pythagorean's theorem did not work in space-time. But it was certainly Minkowski that started thinking of space-time as like a thing. Einstein really didn't do that, okay? At least in the beginning. He eventually came around, but it was his old professor back at ETH, Minkowski, at least I think that's right, that had pushed this space-time image of things, where we think of space-time as like this one thing, okay?
Okay.
Which people always mess up, especially in like popular science and stuff like that. They think that space and time are somehow equivalent or not. Time is not the same thing as space. For starters, they don't have the same dimensions. Now here they do because I've made c1, right? So t equals x, that's seconds equals meters. That's kind of weird, but it's because we set the speed of light to 1. which we can always undo at any point. All right, back to this. So this is not going to work. So we have to think, what could we possibly do that might fix it? Well, if you look at this, the fact that this exists goes back to this right here. Minus 2vxt minus 2vxt. If only that was minus 2vxt plus 2vxt, okay? Then they would cancel, right? Because minus a plus a is just 0. Goes away, right?
Yeah.
This 1 plus v squared almost looks like, remember gamma. Now what is gamma again? Or rather, what is gamma squared? Well, gamma squared is 1 over 1 minus v squared, okay? So if this was 1 minus v squared, we'd be onto something, because that would be the same thing as, well, what is 1 over gamma squared? If gamma squared is equal to 1 over 1 minus v squared, then 1 over gamma squared is equal to 1 minus v squared. You see that?
Yeah.
So if this was a negative sign here in front of the velocity, then this would just be 1 over gamma squared times gamma squared is 1. Gamma's gone, okay? So let's go back and make a sign change. Seems to be an awful waste. Can I save anything? I'm not sure. Maybe we can save stuff from here on. Here's the sign change we're going to make. We're going to get rid of this plus sign, and we're going to make it a minus sign. Now we're going to say that the new, Pythagorean theorem is x squared minus t squared. Weird, right?
Yeah.
Excuse me. Let's see where it takes us. All right, well, this substitution would still stand, but this would become a minus sign, okay? I probably should have left all that stuff up there. It would have been a little easier just to put the signs in than redoing the work. And then when I multiply this out, I still have x squared, and I still have plus v squared t squared. But here I'd have minus 2vxt, that would stay. But here it would be different. This would become minus t squared, right, because of this negative sign here. This would become minus v squared x squared, and this would become positive 2vxt because of this minus sign, right?
All right.
You square this out, you'll still get t squared plus v squared x squared minus 2vxt, but now you multiply all of those terms by a negative and you turn the sign on, right?
Yeah.
So this becomes positive. Look at that. Minus 2vxt plus 2vxt, those guys cancel, they're gone. Okay?
Yeah.
Now here's where it really gets nice. Now let me collect terms again. Put the gamma squared back. Let's collect the like terms. I'll put the x squared here. Where's the x? Here's the x squared. Minus v squared x squared. See it? That's one grouping. That's the x squareds. Now let's get the t squareds together. That'd be plus, I'm going to write is minus t squared plus v squared t squared. Okay?
All right.
And I got rid of these guys. This and this just canceled, right? So those are all my terms. But look, I can do something here. I can factor out a negative out of this, right? Well, actually, let me do it when I pull out the t squareds. Right? I've got the t squareds here, right? So that gives me gamma squared times, pull out the x squared times 1 minus v squared. Look at that. Didn't we want that? 1 minus v squared? Remember, 1 minus v squared is 1 over gamma squared.
Yes.
And then I'm going to pull out a minus t squared, right? Minus t squared times, well, minus t squared times 1 will give me this term back, right? So there's a 1. And minus t squared minus v squared will give me back plus v squared t squared, right?
Yeah.
So minus v squared here as well. See, if I multiply through by minus t squared to here, that becomes plus v squared t squared, which is what I had originally, right?
Yeah.
So that looks good. Now we can do that same thing we did before. We can factor out the 1 minus v squared, right? And I'll get, well, actually, I don't need the brackets anymore. I'll get 1 minus v squared times x squared minus t squared. Okay? Look at this. 1 minus v squared, that's just 1 over gamma squared. So this becomes gamma squared times 1 over gamma squared times x squared minus t squared. Well, these gamma squareds just cancel. I'm left with just x squared minus t squared. Right? That's exactly what I wanted to show. You see?
Yes.
So this is the new length measurement in spacetime. It's not the usual Pythagorean theorem, x squared plus t squared. It's x squared minus t squared. Let me just throw in one caveat, just in case you run into it. I know we've really only worked in one spatial dimension, x, right? But you can have a y and a z. You can have 3 spatial dimensions in here. And as far as the 3 spatial dimensions are concerned, you still use length measurements with the Pythagorean theorem. It's only if you mix time into it. If you have a point which is between 2 different times, okay?
All right.
Where you use this new metric. Terms are very specific, especially in relativity. And so if I say metric, which just means measurement, metric actually refers to a very specific thing in special and general relativity. So I don't want to say that word, but I think they call this the Minkowski version of Pythagoras' theorem. I don't know. It's the way we measure distance in space-time. Let's just say that. I know what they call it. This is the term I think everyone would probably use. They call it the invariant. Okay?
Okay.
Why? Well, as you can see, it's invariant, right?
Yes.
It is the same in both. Okay? And we're not going to go into a great deal of detail about what we do with this. It is important, but not for the kind of stuff that we're doing in this introductory class, right? But I do want to use it tomorrow for our last special relativity lecture on mass, okay? Because it allows me to avoid, I can make a kind of wishy-washy explanation behind Einstein's famous mass equation equals mc squared, okay? Usually you have to have calculus to do this because we'd have to do an integral, and well, we don't have that at our disposal, so we have to find another way to get it in there. And we're going to do it using the invariant, okay? And a little bit of hand waving, and doesn't that seem like a logical idea kind of stuff, okay?
Okay.
But we're not there yet. But that's why I want to introduce this. But I will show you a little bit about what it does tell us and what it means, okay? But first, everyone has taken algebra. Everyone knows what this equation is, right? This is not relativity. Everyone remember what that is? What is it? Is that an ellipse?
No.
No. Ellipses are like circles. It's plus, right?
Yes.
What do we call that thing?
Hyperbola.
Hyperbola. Very good. You're so smart. Yes, this is the equation for hyperbola, okay? X squared over a, or x over a squared minus y over b squared equals 1. And remember that this has vertices at a comma 0 and at 0 comma minus a. I always mess that up. No, silly. Minus a comma 0, of course. That's what the vertices of this are. And it has asymptotes at y equals b over a times x and y equals minus b over a times x. Right? And that's typically how you would graph these things, right? Once you get the vertice down, right, then so vertice, let's say, then you draw in your asymptotes, right? So that you say, well, here are the asymptotes for this guy, and then you just kind of sketch in. You make the hyperbola. That's a terrible hyperbola. I will try to draw prettier hyperbolas, but that's the general idea behind it, right? How you do that. Now, in our case, what did we have? We had x squared minus t squared. And I'll just set it equal to 1. Okay, it can be equal to any number, right? That means that a and b are the same, right? So it's symmetrical in that sense, okay? And it means that b over a is 1. Well, how perfect, right? So that means that what we have, in our case, looks something like this. I'll draw my x and t axes here, okay? And I'm going to draw my asymptotes, y equals x and y equals minus x over here. Okay, there are my asymptotes, yes?
Yeah.
Now, before I draw in any hyperbola, is it hyperbola or hyperbolae? That's a tough one, or hyperbolas, I'm not sure. Let me point out there are 3 cases that we want to consider. And I'm not going to go into any great detail on it, but I think you'll see the idea. The first kind of coordinate that you might get, if I put a point right there. So on that dotted line, okay, remember that in a space-time diagram, a light line emanating from the origin has slope 1, so it is a 45-degree line. It is right on top of that asymptote. Do you see that?
Yeah.
Yeah. And so that, of course, is given by the equation that x equals t. And so case number 1 are light-like coordinate. I'm just going to write coord. Okay, this is when x, I'm going to call it delta x because it's always a delta, right? Delta x is equal to delta t. Okay? So in terms of this equation here, right, you say, well, all right, well, if delta x is equal to delta t, that means that delta x squared is equal to delta t squared, which means that delta x squared minus delta t squared is equal to 0, right?
Yeah.
But light-like coordinates are points in space-time that would lie on a light line with respect to an observer at the origin, okay? So we have to imagine, in all of these cases, that we're standing at the origin and observing, okay?
Okay.
And so this point here is a point that can be reached by light. Okay?
Okay.
This will make more sense when I get to the next thing. The next thing we want to consider are what are called timelike coordinates. That's a timelike coordinate. Anything that's above this v or below this v is called a timelike coordinate. okay? And in that case, what we write is this. We write that delta t, well actually we call it tau, okay? If we're talking about time-like coordinates, our x squared minus t squared is, we'll name it, we'll call it tau squared, okay? So we'll write delta tau squared is equal to delta t squared minus delta x squared, and we'll say that this is always greater than 0, okay? Notice that I move the time in front, okay? This means that delta t squared is always greater than delta x squared. So whatever time you travel, this distance is greater than any distance you travel in this direction, you see?
Yes.
These are points that you can reach in time. You can access by traveling there. I could, for example, put myself, I could boost into a, we never use that term, but if you start moving, you now consider that you draw a boosted frame. And the boosted frames are these ones that make an angle to the light line that we've been working with. So if I consider that point there, I could draw this boosted frame like this, okay? T prime. Just the thing we've always been using, right?
Yeah.
Means that that point can be accessed by this boosted coordinate, right? It also means that this delta tau squared, whatever that number is, right? It's greater than 0. Whatever it is the proper time in this particular frame. You just draw a straight line from the origin to that point, and that represents a uniform motion frame, a train you can jump on, that will get you to that coordinate. It's not the same as accessing a place in the room, okay?
Okay.
Because time is always going forward. You're always going up, all right? This point is always getting closer, okay? And in order to get from here to this distance that you need to go to arrive at that point, and in time, you have to travel with some velocity. I know it's not the easiest thing to think about, but it is. This turns out to be, this is your future, okay? And this is your past. Everybody has a different future and a different past because we're not standing in the same location at the same time.
Yes.
Weird, huh? There are space-time points that I can access that other people couldn't. Kind of. There's the helicopter. It's like on cue, isn't it? Does that helicopter go by every day? I don't know.
Pretty much, yeah.
Wonder who it is. So this is your future. This is your past. All the places inside this light cone, that's what it's called, the light cone, are places that you can access. Okay? You may have to travel at some velocity, but you can get there. Okay?
Okay.
And that brings us to spacelike coordinates. That is a spacelike coordinate. Right?
Yeah.
If you are here, you will never arrive at that. You will never be able to witness that event. Think of these not as locations so much as events.
All right.
Okay? Something's going to happen there, right? So if you call it an event, now it makes it important that not only are you at that spatial location, but you're there at the right time. Because if there's a party, right, and you show up a day late, you didn't really go to a party now, did you?
You did not.
Yeah. And so that's what happens here. These are parties you can never go to, okay?
Okay.
And we change the symbol we use. We call it delta S squared. Your mother told me why we call it S. It's a German word. Anyone remember the German word?
No.
It's like a stretch. Like, it doesn't mean distance per se, but it's like, in English we would say, I'm going to walk for a stretch. And whatever this German word is, I will try to figure out what that word was. I can't think of it. Anyways, it's a German word, and that's why we call it that. And so we call it delta S squared. And this call it delta S squared. And this time we set it equal to minus x squared, delta x squared minus delta t squared. And this is always greater than 0, okay? So I've switched the signs around, you see?
Yes.
Now it's the x that's in front and the minus the t, right? And these are points that you will never get to, okay? It's beyond your reach. You have to travel faster than the speed of light to access that event, okay?
Okay.
Does that make sense?
Yes.
Okay. Distance, this delta S squared term is called a proper length. You will be able to find, however, a line of simultaneity, right? So let's say I boost myself, okay? I will be able to find a line of simultaneity that passes through that point. Okay? I just can't be there at that time, you see? Because
Yeah.
these axes you're always going forward in time. Now one of your graduate students that you have posted up, he gets to go to the party, but you don't. Okay?
Okay.
All right, let me show you one more little thing with it. And again, you can, for example, demonstrate using the hyperbolas, which I haven't even drawn yet. I drew the light cone, and I showed you what your past was, what your time-like coordinates were. right? Unfortunately, I erased it, but in that instance there, right, the spacelike coordinates on the positive side, you call that your right, I guess, or maybe your left if you're facing the other way, and the other side is your right. You've got, and then in the spacetime, up was your future and down was your past. Now, when you have all three dimensions, spatial dimensions, the light cone really will be a cone. It'll look like a cone in these three dimensions, right? But the spatial part will wrap all around you, okay? It's a little hard to draw on the board, or otherwise I'd attempt it. But you can look on the internet, there's plenty of good pictures that represent that well. Okay, let's consider this. Let's let delta tau squared be equal to 1, okay? So that means a proper time interval of 1. Let's let a clock tick for 1 second, 1 minute, whatever, 1 hour, okay?
Okay.
And so we know that that will be equal to delta t squared minus delta x squared, okay?
Okay.
But it will also be equal, because it's invariant, to delta t prime squared minus delta x prime squared, right?
Yeah.
This is the same in both. So let me show you what that looks like. So we draw our x and t axes. Let me draw our boosted frame now. Well, actually, let me draw my light cone. In general relativity, it's more common to just draw the light cone, and you don't even draw the other coordinates. Here's your observer, there's your light cone. So the light cone, which is also the asymptotes of these hyperbola, which I haven't drawn yet. Okay? And let me draw my t prime now. Well, actually, first I'm going to draw the hyperbola. Okay? So here is the point 1. Okay? And the hyperbola, it will approach that to infinity. Okay? It's a little better hyperbola. And so this point here, call it A, this is the proper time of, say, 1 minute in the platform frame. Okay? I'm just the guy at the origin. I stand there. I wait for 1 minute. I find myself at event A. I clap my hands. That's the event. All right?
Okay.
Where is event B? Well, it depends on how much you boost. Okay? What's your velocity? Let's say that I'm going a modest speed, maybe 80% the speed of light, something like that. So my t prime axis will look like this. Okay? T prime. I'm not going to draw the x prime axis because I don't need it. This point here, where it crosses the hyperbola, okay, that's point B. That also, every point along this hyperbola has a delta tau squared equal to 1. Okay? That means that in this boosted frame, this distance you see here, that is a clock ticking for 1 minute. Okay? This here, from the origin to this point A, that is a clock in the platform frame ticking for 1 minute. All right?
All right.
And you look at these two distances and you're like, okay, well this distance here is like this, and this distance looks longer, but in special relativity they're the same length. Okay?
Okay.
So this is why a lot of relativity problems are misleading. You remember back to the twin paradox, just one last thing. Twin paradox, we had the twin travel out and then he traveled back, right?
Mm-hmm.
And you're like, okay, well that's interesting. If you look at it, you think about it, you're like, well I see two right triangles here if I draw a line in here like that, right?
Yeah.
And make this my right angle, right? Now I use my Pythagorean thinking, and I think, all right, well this distance here is less than this distance here, yes?
Yes.
By the Pythagorean theorem. This is actually the shorter distance though. Why? Because of this. Pythagorean theorem is the wrong metric to use. This distance is less time than this distance. Even though it looks longer, it's less.
All right.
Okay? And so that's one of the pitfalls people fall into with special relativity, especially when they draw pictures, is they think that their intuitive sense of distance means something, and it doesn't. Okay? That's why when you work with it, you got to have the Lorentz transformations, memorized, so that you can get the right numbers. Okay? Or you can use the hyperbola. It's not hard to show, say, like time dilation. I mean, we're pretty close. All we'd have to do is write a couple of things down, and we'd be there with time dilation. We could get the time dilation equation that delta t squared is equal to gamma times delta t prime squared, right? That would be very quick. Length contraction is a little bit harder. It has a couple of steps that you have to do. But I'm not going to show it to you because we're not going to use it for anything. We are going to use this metric, though, okay? This delta t squared minus delta x squared, we're going to use that in the next lesson. Any questions about the invariant hyperbolas? You could draw a spacelike hyperbola over here, right? You pick some spacelike interval, right? Where are all the distances that are equal to, 2 meters, right? So that's 1, 2 meters, right? You could draw the hyperbola for that, and then when you drew your boosted x prime axes, right? There we go. Here's x prime. There we go. That's 2 meters there. So this longer line is the same length as this what appears to be shorter line. Okay? Because wherever any point along this line, right, is 2 meters in space-time distance. Okay?
Okay.
Any point along this line is 1 minute in space-time distance. Okay? All right. I think that is it. Unless you guys have questions. Anyway? No? Okay.
Oh, wait. Will we have homework on this? Or
This? No. I don't think so.
what's the triangle on the right side there?
That?
Yes.
This was the twin paradox problem that we looked at last time, right? The twin travels out, and then he comes back, right? He finds that his brother has aged. He found that this time here is less than the time that he experienced when he was traveling, okay? That's kind of the way to think about it, I guess, is that whenever you speed up, right, you're taking, if this is my velocity vector, I'm not moving because I'm just going forward in time. I'm just standing still, okay? As soon as I give myself a velocity, right, it's kind of like I'm losing a little bit of time in order to gain some space, all right? And there is a clever way to think about that in terms of these invariant hyperbola, but I think it's, you have to work with this a little bit more to become fluent with it, and with that kind of intuition would make some sense. So I'm not really prone to go down that road, but that's the general idea, though. You get some velocity, you're kind of trading off a little bit of time in exchange for some space, all right? If you go fast enough, right, time, people like to make a big deal out of this, but photons, right, time doesn't exist for them. Right, this tau squared, when x is equal to t, right, delta x squared minus delta t, or t squared minus delta x squared is 0. That means that time is 0. Proper time is 0. A clock in that light reference frame would be 0. It doesn't tick.
All right.
And I don't know, maybe I think there was this Einstein story about when he was a kid imagining trying to catch up to a light ray that reflected off of the clock, right? So the light ray reflects off the clock, and you can imagine that there's this light ray that says, 12 o'clock. And it's, running out and headed out that way in the universe, and if you could just run fast enough, you could catch up to it. And if you did, and you matched its speed, then you'd be standing at 12 o'clock forever until you decided to slow down, right? And maybe, presumably, you could speed up and maybe get yourself to 11:59 and 11:58, and here come a lot of the, the science fiction ideas about time travel into the past. None of them will work, of course, but you can't travel faster than the speed of light. But you can travel forward in time, and so maybe it's a little bit like running after those light rays. All right?
All right.
Maybe, but I tend to trust the things that we can measure and calculate and draw, and All right, that's it.